This is section 3.8, part B. We've been looking at solving equations that contain logarithms. Now we're going to look at equations that contain exponentials. Eventually we'll have two different ways of doing this, but for right now, this is what I'm going to call method 1. First of all, we need to isolate the exponential, get it by itself on one side of the equation. We'll then apply the logarithm function that is the inverse of that particular exponential, the one with the same base. We should get an equation that we can solve for x. Always keep in mind, do the same thing to both sides of your equations, and do check your solutions to make sure you don't have any extraneous solutions. By the way, when you use your calculator to find logarithms of an arbitrary base, on the TI-84, in the math menu, if you scroll down a little ways, you will find this option here that says log base. That's what we'll be using when we do our logarithms. So just to practice, let's try this out. If I want the logarithm base 2 of 8, it gives me 3. Hopefully you expected that, because when you think about it, 2 cubed is 8. So did we expect this? Yes, of course. All right, what about one that we couldn't do in our heads? The logarithm base 6 of 82. I can't think of any power that I could raise 6 to get 82. It's undoubtedly a number that doesn't come out nice and evenly. So we're going to go back to math again and choose log base. And I want the log base 6 of 82. And it's about 2.459. To answer the question, does our answer make sense? Well, this is a number between 2 and 3. 6 squared, we know, is 36. 6 cubed, either you know or you can do it on your calculator, is 216. And since our number, 82, is in between 36 and 216, it makes sense that our answer is going to be between the 2 and the 3. So it's logical, even though we maybe couldn't have come up with it on our own. All right, so let's follow our process now for solving equations with exponentials, keeping in mind that when we need a log base, whatever, we'll use the calculator to get it. First of all, I have 8 to the x equals 1,000. 8 to the x is my exponential, and it's already isolated. So I'm going to apply the inverse function, which would be the log base 8. I have to do that on both sides. And on the left side, the log base 8 and the exponential base 8 are inverse functions. So when they act on each other, that just leaves me an x. And on the right-hand side, here's where I need that log base function. The log base 8 of 100 is 2.214. It says round to 3 decimal places, so that's what we'll do. 2.215, actually, I guess, if I round. And that really is an approximation. So it says give both an exact answer. I probably should have read the directions first, huh? Give both an exact answer containing a logarithm and also an approximation. This was our exact answer, the log base 8 of 100. Our decimal approximation is 2.215. All right, let's try another one. Here, I'll notice that my exponential is not yet isolated. 5 to the x power is the exponential. And I'd like to start by getting that by itself. So let's add the 4. And then we'll divide by the 3, giving us 5 to the x power equals 9. This is something that I can now use the inverse function, the log base 5, to get to the x. So let's do that. The log base 5 of 5 to the x is equal to the log base 5 of 9. Again, I've done the same thing on both sides. I've taken the log base 5. Of course, we chose that because it was the inverse of the exponential base 5. And that just leaves us x. Our exact answer is the log base 5 of 9. And then I could also do a decimal approximation on my calculator. And get about 1.365. So there's both the exact and the approximate answers. All right, let's try one more like this. (15 equals 4 to the 2x minus 5 power. Now the exponential is already isolated. This is one base with an exponent. So I can go ahead and do my logarithm right away. The exponential is base 4, so I'll use the inverse, which is the log base 4, on both the left and the right. Because I need an exact answer, for right now I'm going to leave the log base 4 of 15 the way it is. Later on, when we go for the approximation, we'll get the calculator going on that. Oops, and I guess I don't need that yet. Log base 4 and exponential base 4 are inverses. So on the right-hand side, I just have 2x minus 5. I'll add the 5 to bring it over here. So I have the log base 4 of 15 plus 5. And if it's okay with you guys, I'm just going to go ahead and divide by that 2 at the same time. So there's my exact answer. I can get the decimal approximation on my calculator. I'm going to use my little alpha y equals and get a fraction. The very first option just makes it a little easier to type this in. Lots going on here. Log base 4 of 15 plus 5 divided by 2. And it's about 3.477. And again, to do that, it was the alpha y equals that gave me that fraction template. I don't know if I've used that yet, so if not, there it is. And there we go, exact and approximate solutions. All right, we've been able to solve these three equations by hand, but there are times when we cannot solve an equation by hand, either an exponential or a log. If the variable appears both inside the log and outside the log, you're not going to be able to solve by hand. If it is inside the exponent and also outside the exponent, you're not going to be able to solve by hand. In those cases, remember that it's always possible to solve any equation, at least get real solutions, using a graphical method, a calculator or Desmos. By graphing both the left side and the right side. So we'll graph y equals the left-hand side and y equals the right-hand side. We look for where they intersect, so we find the intersection. And since we're only solving for x in these problems, we'll only use the x value. And keep in mind, this does only find the real valued solutions. We really haven't been coming up with imaginary solutions to our exponential and log problems anyway, so that shouldn't be a big problem. All right, here are a couple of examples. If I'd like to solve the equation 1/5 x equals log of x plus 4, I'm going to say right away that there's no point in even trying this by hand because I see here's an x that's not in a log, there's an x that is in a log. When I've got both of those, I know I'm not going to be able to solve by hand. So let's come on over to Desmos. And I'm going to go ahead and put in y equals the left-hand side, which was 1/5 x. And then also y equals the right-hand side, which was the log. Whoops, I didn't put my y equals in there. Desmos doesn't honestly care that much, but as a mathematician, it bothers me. There we go. I don't have a very good window here, so let me just go ahead and reset this. For now, I'm going to go a standard window, -10 to 10 on both axes. And that's not too bad. We'll notice there's an intersection point right here. That one's got the x value of -3.828. Remember, I'm solving for x, so I don't really care about the y here. And then this one is a second intersection point. X is about 4.697. So I'm actually going to take a minute while I can still look at this and jot those down. X is approximately -3.828, and x is approximately 4.697. And there we go. I'm going to use a similar technique on problem 2 here, because once again, notice this x is in the exponent, and that one is not. That tells me right away I'm really not going to be able to solve by hand. So I'll set up my Desmos graphs again, letting x or y equal the left-hand side and y equal the right-hand side. So let's see. First of all, y equals 3 to the x. Oops, wasn't on there. Let's try that again. There we go. And then secondly, the right-hand side, y equals -x plus 5. And in this particular case, I can see it looks like there's just one intersection point right there. X is about 1.212. I always want to think about would there be any others, but knowing the nature of these functions, my linear function's not going to change directions, and the exponential is going to keep going up as well, so I can kind of visualize that there wouldn't be any additional ones. So just one solution this time. X is approximately 1.212. All right, that brings us to the end of Part B.